so we got into really chapter 2, which is really sort of where the class sort of really begins. And we started talking about units and measurements a little bit. Remember, as we talked about that, always when we do a measurement, as we talked about, you always need a number and a unit. They should always go together. And as we talked about, when we talk about showing work here in chemistry, this class, future chemistry classes, units seem to get lost a lot of times in the calculation part of it. You should always have units in your calculation part of it as well, not just like the final answer or anything like that. So just get into a habit if you are not into that habit to make sure that you do include the units as we go through your work. And also, we talked about really two types of units, kind of the English system or the US system and the metric system. And again, it sort of came together in science with the SI system, which is really based off of that metric system. And it's important also in terms of including units in your calculations and also your measurements for sure. That you understand, again, as we talked about, what those units do represent. Do they represent a volume? Do they represent a mass or whatever it may be? So last time we got into a little bit of some length measurements and we got into some volume sort of units. So we're going to pick up here with mass, which I think is the next sort of type of unit that we come across. Mass is the quantity of matter that's present in an object. Matter basically is anything that occupies space and has mass associated with it. Is pretty much everything. As we'll talk about in, I think, chapter 3, next chapter, there's 3 states of matter. There's solid, liquid, and gas. And really, you know, a lot of what we look at in chemistry is sort of how we change from these different states along the way. But when we talk about mass, the fundamental unit of mass is kilograms. And a couple sort of conversions or qualities that are important that you use a lot, and that is our 1,000 grams is a kilogram. That is used a lot in chemistry, and you'll see it a lot. That is also, like we talked about last time, like the kilo sort of prefix there that we saw in that table, which was like 10 to the 3. Also milligrams as well. There's actually 1,000. Looks like 6s. 1,000. There we go. Milligrams in 1 gram, as the milligram is a smaller sort of value there. Get rid of make those zeros. So I would say definitely in chemistry in terms of sort of units associated with masses, grams especially use a lot. Kilograms and milligrams are very, very common sort of mass type of units. As we talked about last time, as I'll mention a lot as we go through here, again, reminder that in this class, they essentially don't want you to be given anything. So these are definitely some conversions that, again, you should probably commit to memory because you will use it a lot, definitely in this class. Now, there is a difference between mass and weight, and sometimes people sort of use it interchangeable. But specifically speaking, weight refers to the force of gravity that exerts itself on an object. Mass is sort of independent of the force of gravity. So when we weigh something, which is really the process that we use to get the mass of an object, you should refer to it usually in chemistry and sciences as the mass of the object and not really the weight of the object. So when you go to balances like we saw in the lab room the other day, in the back there, you are getting the mass of the object is really what you should record and really not the weight. Yeah.
Like, you're affected by gravity though? So what did you say that basically mass have a weight?
Yeah, so we refer to sort of getting the mass of the object. Thank you very much. Not taking into account the force of gravity. When we, for example, your weight would be different here than say like on the moon, which has obviously a different gravitational force and stuff like that. So it's just common here that we refer to it as, obviously, there's obviously gravity here, but we refer to it as the mass of the object, yeah. And that's sort of the difference between sort of, the idea of mass and weight as well. Other questions? So let's talk a little bit about temperature. Temperature we use a lot in chemistry, obviously. A lot of formulas involve temperature. And there's really sort of three different temperature scales that we refer to. We have the Fahrenheit scale, which is degrees Fahrenheit. And that is where water boils at 212 degrees Fahrenheit, freezes at 32 degrees Fahrenheit. That is the scale we use for like our temperature, the outside weather, all that good stuff here in the US. The Celsius scale is used, and that's more of a metric type of system, and that's degrees Celsius. And on the Celsius scale, water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. Those are two numbers that you really should also know. Again, where water freezes and boils on the Celsius scale, those numbers are used a lot in chemistry, and they kind of pop up, and you see some of those numbers in some calculations. A third temperature scale, which you might not be too familiar with, is the absolute temperature scale, later renamed the Kelvin temperature scale. And it is Kelvin here with a K. And on that scale, water boils at 373 Kelvin and freezes at 273 Kelvin. Now, there is a difference in terms of how we also write the symbols. For Fahrenheit and Celsius, we do include the degrees sort of symbol. For Kelvin, we do not. So it is just Kelvin. So it's something like 373 Kelvin. It's not 373 degrees Kelvin or anything like that. So we don't use the degrees sort of symbol there for Kelvin, but we do use it for the others. The way that we convert between these, that we'll talk about in just a second here, is based really on the differences in terms of how where water freezes and boils on each of those scales. So Fahrenheit, it's about 180 degree difference, and Celsius is about 100 degree difference. And also for Kelvin, also about 100 of Kelvin difference. And those make up basically how we do our conversions between them. And as you can see here, here's sort of the three different scales. And out of these three, really in chemistry, as I might have mentioned last time, it is going to be Kelvin. That's pretty much the temperature scale that you use most of the time. Pretty much, like I said last time, all chemistry formulas, except for maybe like one or two, you do need to get the temperature into Kelvin before you put it into the formulas. So again, that's almost like an automatic thing. If you're doing something in chemistry and you got like a temperature and you got to use it in a formula, it's almost automatic that you need to convert it into sort of Kelvin before it goes into the formula. I would say probably most of the time, this is going to be your sort of conversion route. You're going to go from Celsius to Kelvin, because oddly, even though most of the chemistry formulas that we use uh, involve Kelvin for the temperature, most of the ways that we measure temperatures in Celsius. So if you look at the thermometer, when you get to the laboratory, your thermometer will be in Celsius and stuff like that. So it's a super common conversion going from Celsius to Kelvin. Probably the next most common conversion in chemistry is going from Kelvin back to Celsius. So kind of going back and forth between those two is very, very common. I'll be honest with you, probably outside of chapter 2, you probably won't see too much of Fahrenheit popping up in chemistry and stuff like that. But definitely temperature values are very often given to you in Celsius, and very often you got to take those values, convert it to Kelvin, and then put them into the formulas. So let's talk about how we do convert between them. I do need to edit this here. So let me just do a little quick edit here. To convert the temperature into Kelvin, you will take the temperature in Celsius and you will add 273.15. That's what they want you to use, that entire number. Has a little editing here. So they expect you to kind of use that number there, 273.15. Some people, like in the old lab manuals, they might still have it as like 273.2. outside of this college, perhaps most people will use 273 to be honest. Here, they do want you to use kind of the whole number here, 273.15 to convert it. Obviously, that means that if you do have the temperature in Kelvin and you want it to Celsius, you would take the temperature in Kelvin and you would subtract 273.15. So that conversion, really both of these, which is kind of the same one, just kind of turned around, are pretty much 99.9% of the time going to be really the conversions that you're going to be doing here in chemistry. Now, to go from converting Fahrenheit to Celsius or vice versa, we have a couple other ones. The temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus a 32. That 1.8 is the same thing maybe learned as a fraction, like 9 over 5. So it's the same thing. If you take 9 divided by 5, we get 1.8. So it's the same idea. And if we want our Celsius temperature from Fahrenheit, we take temperature in Fahrenheit minus 32 divided by 1.8. So again, these guys in boxes, you should know how to do those. They will, again, not be provided for you. So you got to make sure you know how to convert them. So when we're doing temperature conversions and we're only really doing temperature conversions, and that's, kind of the only thing we're doing, we do follow sort of a general rule for sort of significant figures and what your answer should have. We're going to talk more a little later on in this chapter about significant figure rules and calculations and all that. But temperature is a little bit different in terms of what you generally do when you're doing a conversion. So just specifically for temperature, when you're doing any type of temperature conversion, your answer should look like the original temperature. So what do I mean by that? What I mean by that is if the temperature value you're converting, and again, all you're doing is just converting it from one temperature scale to the next, let's just say it was a whole number. When you do the conversion, you would convert it to a whole number. If the original temperature value you had went to one decimal place and you're doing a temperature conversion, you would do the conversion to one decimal place. So the general rule for temperature, it doesn't follow really strict significant figures sort of rules. Because there's a lot of variations, like 1.8 people will use, 1.80, 9 over 5. So there's a lot of variations in terms of maybe the formulas that people will use. So most of the time people will follow that general rule, which is essentially whatever the original value went to, whole number, one decimal place, two decimal places. If all you are doing is converting those temperature values into another unit of temperature, you keep it the same. Any questions about there? All right, then why don't we try some? So grab your calculator, do these conversions, see what you get here. Okay, so let's take a look and see. So first off here, we have the temperature in Celsius. So we got degrees Celsius. We want to go to Kelvin. So a reminder that the temperature in Kelvin will equal the temperature in Celsius plus our 273.15. So putting in our number there, 28.5 plus a 273.15, that's going to get us here 301.65 Kelvin. Now, in terms of where we should go with our answer, again, our original number here went to one decimal place. So here we would round this guy to 301.7 Kelvin in this case. Any questions on that there? Okay. So when we look at the next one, which is Celsius, going to degrees Fahrenheit, our temperature in Celsius will equal our temperature in Fahrenheit will equal our 1.8 times our temperature in Celsius plus a 32. And put in our numbers there, 1.8 times 41 plus a 32. Again, we put this in our calculator, 1.8 times 41 plus a 32, going to give us a 105.8 on our calculator, degrees Fahrenheit. I keep wanting to say Celsius. Degrees Fahrenheit, yeah. Are you always supposed to round for the answer? Yeah, so whenever you do any type of calculation, you should round it to the correct number of significant figures. And we're talking about specifically significant figure rules a little later on in the chapter. But for our temperature, we do want to round, generally speaking, if you're just doing temperature to what the original number looked like. So that's why on the original one here, we had 1 decimal place originally, so we want to take it to 1 decimal place. Yeah. Right, so temperature conversions don't follow strict significant figure rules because of the conversions, the sort of formulas that you use to do them. There's a lot of variety in terms of what people might use. For example, the first number here, most people, I'll say outside of this college or this department here, will use 273 for the Kelvin conversion rather than 273.15. So because, for example, here they use 273.15, everybody else probably would use 273 but without the 0.15. There's a lot of variations on that, including the ones for like Celsius to Fahrenheit as well. We use, for example, 1.80. Some people will use 1.8. Some people use the fraction 9/5. So because there's all that kind of variations, what they've done is kind of come up with like a general rule only specifically for temperature conversions where you're going from temperature to temperature. And basically the rule is whatever the original temperature value looks like, that's what you want to make your end result is. Yeah. When we get into real calculations or sort of real significant figure rules, there's specific rules you should follow that would follow those. Yeah. Other questions? Okay. So last one. Oh, we didn't get this one. We do want to, when we look at this is going to be a whole number. So in this case, we do want to actually round this guy to a whole number, and we will end up with 106 degrees Fahrenheit at this point. Yeah. Questions on that? All right, the last one, we're going from Fahrenheit here to Celsius. I could probably write it right now. So here, temperature in Celsius, this is our Fahrenheit minus a 32 divided by 1.8. So put in our number in there, 160 minus 32 divided by 1.8. Gonna get us here 160 minus 32 divided by 1.8. We're gonna get like a kind of like a 71.111, a bunch of ones on your calculator there. Once again here, looking at our original value, it is a whole number. So here we would actually take it to the whole number as well. So again, these sort of rounding here for temperatures, the way we're doing it for this is specific for just temperature to temperature conversions. So there definitely is different rules for all other calculations pretty much. Any questions on temperature conversions? Bless you. A reminder again, you do need to know those formulas as to how to convert it. And here at this school, they want you for all your chemistry classes to use something like the 273.15. Again, you may see it around other places where people kind of round off that 0.15, but they do want you to use the whole sort of number here. All right. All right. So when we look at these units, again, as we talked about, it's important to know what those units represent. So when I see 523 Kelvin, that should be a temperature, right? When I see 25.36 liters, that represents what type of measurement? That is a volume, right? 15 meters is distance or length, and kilograms is a mass. Yeah. So again, as we talked about, it's really important to understand what those sort of units represent in terms of their sort of quantity there. All right. So let's talk a little bit about a couple of different types of sort of measurements and our observations. So when we talk about qualitative sort of observation, qualitative basically means that you have general observations about a system. it's really not a measurement at all. So it's just like, hey, the thing's purple, there's some bubbles happening, rainbows happen, whatever it may be, as you're doing whatever you're doing. So qualitative is more like a descriptive type of observation. There's really no measurement involved. In fact, for example, if you continue on to 1B, you do a bunch of experiments which are known as qualitative analysis. And in those experiments, just to illustrate that there's no measurements, you don't measure out volumes, you just go like, 20 drops seems about right. There's no like mass measurements or anything like that. It's just like you add things, you go, oh, I got like a yellow precipitate, or the solid disappeared, or things like that. So qualitative is more, again, these sort of general observations. They are not rooted within a measurement or anything like that. And that's different than quantitative. Quantitative basically is measurements. So it comprises of numbers and values that you get from some type of measurement. So when you do go to the balance and you record 32.56 grams, that is a quantitative measurement of the mass. When you use something like a graduated cylinder to fill it up with some liquid to a specific volume, you're quantitative filling that thing up to get to an actual value that you're looking for, be it 5 milliliters, 10 milliliters, 12 milliliters, whatever it may be. So qualitative, more observations, no real measurements. Quantitative, all about measurements. So let's talk about also an important sort of way that we write numbers or see numbers sometimes in chemistry, which is scientific notation. And scientific notation is basically this formula here, n times 10 to the n, where this is a number between 1 and 10. And this guy here, again, is positive or negative, depending on sort of which way you need to go to get a number between 1 and 10. By the way, the first number can be 1, but it can't be less than 1. So it can't be like point something, the first number. And the first number can't really be 10 or above. So it can't be like 10, 20, 100 or anything like that. It's got to be really less than 10 and kind of 1 and above on that first number. We use it really for really large numbers or really small numbers. As you can see there, the mass of a hydrogen atom is 0.000. I lost track of the zeros already. And the mass or the distance to the sun is like 93,000,000. So you can imagine, obviously, if you kept all those zeros, either a really small number or a really large number, and you're trying to do some type of calculation, you most likely will lose some numbers along the way. So that's really where scientific notation is helpful. If we had something like 423, we assume that the decimal point would be here, even if it's not written, and we go one place, 2 places to the left, and that gives us a number of 4.23 times 10 to the 2. Here we move to the left, and we end up with a positive exponent. If we had something like 0.003345, here if we went 1 place, that would not give us a number between 1 and 10. If we go 2 places, that's 0.3. That is not a number between 1 and 10. We need to go 1 more place and get 3.345 times 10 to the minus 3. So if you have a number sort of written in positional notation or decimal sort of form, and you need to turn it into scientific notation, you basically move the decimal point to the left or to the right to get yourself to a number between 1 and 10. And again, it can be 1. It cannot be 10, though. So it's got to be somewhere between those 2 numbers. Yeah.
So safe to say that the exponent is going to be a number of places.
That's exactly what it is. So it's basically the number of the exponent is how many places you need to move that decimal basically to get to a number between 1 and 10. So if you just want to remember it this way, large numbers above 1 have positive exponents, yes. Small numbers below 1 have negative exponents. So if you move it to the left, it's going to give you a -1. It's going to give it to the right, a positive 1. Also works the other way, right? So, if we had a number, say, in scientific notation, and we want to turn it into decimal form, if you will, or positional notation out of scientific notation. Positive 3 means it's a large number, and that means I actually need to go this way to get a large number because that will make it like 120. If I go the other way, it's not going to be a large number. It's going to be like point something, right? So that's going to be a smaller number. So we go 1, 2, and 3 and throw some zeros in there, and we would end up with, 1200. And that would be our number out of scientific notation. If we had 1.3 times 10 to the minus 2, same idea here. Minus means small number. To get a small number, we need to go to the left because that's like 0.1. If we go to the right, that's 13, right? So that's a larger number, so we don't want to go that way. So we go 1, what do we got there? 2. And 2, we'll throw a 0 in there, and 0.013 would give us our number sort of out of scientific notation. By the way, when you do write a small number that's like a decimal, it is also really important to include the kind of 0 before the decimal point. It's very proper to do that so numbers don't run together and stuff like that. So if you got something that's like a point something number, you should put that 0 before you do it there in that particular case. Any question on that there? Do you have to write the numbers in scientific notation all the time? You do not, but as we will talk about, there is sometimes only one way that you can sort of properly give an answer to the correct number of significant figures is to write it in scientific notation. So sometimes the only way they kind of give the answer correctly is to put the number in scientific notation because that will allow you to get the right number of significant figures. So what do I mean by that? I mean by that when you have a number that is written in scientific notation, say like this, all of the numbers that come before the times 10 part, all those numbers are significant. So this number here would have technically 2 significant figures the way it's written. Doing significant figures off of a number that is written in scientific notation, it is based on how it is written in scientific notation. And what I mean by that is sometimes people will be asked this question, like, how many significant figures does this guy have? And they'll turn it into this like a regular number. They'll turn it back into like 1200 and go, it's got like 4 significant figures, right? And that would be incorrect. So when you're asked a question like, for example, how many significant figures does this number have, and it is specifically written in scientific notation, any number that is written before the times 10 part is going to be significant, and that's how you know. That's also going to be important when we talk about the rules for significant figures and calculations, that if you see a number written in scientific notation, you'll know, oh, it's written with only 2 there. So that is how many significant figures that number has. Yeah. We're actually a couple of slides away from that, and we'll get to it. Yeah. Other questions? So like I was saying a second ago, scientific notation, sometimes the only way to get to the right number of significant figures. So for example, let's just say this was my answer, but our 1200 was my answer, which is this number basically, but I needed it with 3 significant figures. So what I could just simply do is 1.20 times 10 to the 3. Voila, now it has 3 significant figures. Let's say I needed 1 significant figure. I could write this as 1 times 10 to the 3. Whoops, if I could write 3. Now I have 1 significant figure. So writing a number actually in scientific notation gives you some flexibility in terms of I could get it to exactly the right number of significant figures that I need by just sort of adjusting the number that comes before the times 10 part. Yes. Yeah. No, so remember the other really important part is this number here that comes before it has to be a number between 1 and 10. So it can't be like 12 or something like that, or point something. So it's got to be a number between 1 and 10. So it could be 1 and it has to be between 1 and 10. So again, it can't really be 10 either. So it's got to be like 9 point something, kind of deal. So that's also really important because that's sometimes what people will do. They'll go, oh, well, then I'll just do like, something like this, or something like that, type of thing. And that would be technically incorrect because that front number is not between 1 and 10 and stuff like that. So that front number has got to be 1 to 10 to be properly written in scientific notation.
First one, you put 1.2 times 10 to the 3.
Yeah.
But on the second one, you added a 0. So
It's still the same if you convert it back out. So this would be, again, 1.2, 1, 2, 3, right? And then it would be basically 1200. This would be same thing, 1.20, 1, 2, 3, still 1200. So still the same, just different number of significant figures. And as we'll talk about, when you convert that into a regular number like 1200, right? The way I wrote 1200 right there, technically, as we'll learn, has actually only 2 significant figures, which is a problem if you need to give your answer to, say, 3 significant figures, or if you need to give it to like 1 significant figure or something like that. You will have the right answer in terms of number, but you won't have the right answer in terms of significant figures. So this would be a good example, actually, of like if that was the number I got on my calculator, but I know based on the calculation I did, I need 3 significant figures, and I left it as 1200 written like that, it would technically be incorrect based on significant figures. But if you wrote it like, I scribbled on it, but if we wrote it like this, then now it is still 1200, and it has the correct number of significant figures based on the way I wrote it. Yeah. Other questions? Yeah. Yeah. They, there's actually a rule, and we're going to talk about when we get to significant figures in a few slides, but there's rules for zeros. And one of the rules is if there's a decimal in the number, it counts and stuff like that. So because you have to go like a number between 1 and 10, you always have kind of a decimal in it. So those will always make kind of those zeros that are in there, which I think is your question. When it's written in scientific notation, they'll always become significant. Okay, other questions? All right. All right. Now, before we get into all those measurement significant figure rules, let's talk more importantly about scientific notation, other than the fact that you do need to know how to write it correctly in scientific notation. You do need to be able to go from a scientific notation back to a decimal or positional notation type number. But more importantly is how to properly punch it into your calculator. Yeah, so how to use your calculator and scientific notation. That is really important. So when you have your calculator, and if you have it with you, you might want to look at it, you probably have an exponent button, and it's one of these 3 combinations on most people's calculators. You have either an EE button, you might have the classic EXP button, or some of the newer ones, and these are usually, I would say, they're usually 2-tone in color. There's like a main color and like the outside's like a different kind of color. There might even be a times 10 to the n. And usually if you have that type of calculator, you also have like a little wheel type action going on there towards the top. Now, sometimes these buttons will be in different locations. Sometimes the exponent button might be on towards the bottom. Sometimes they're like in this area on a lot of calculators. Sometimes they may be like you got to hit a shift something above it. So there's somewhere in those areas. Now, when we write a number or punch a number into scientific notation, let's just say we're going to do 1.23 times 10 to the negative 3. We want to properly punch that into our calculator. Now, I'm going to talk first off about these buttons here. So if you have a calculator that has one of those 2 buttons, you're good. And we're going to talk about that. Then afterwards, I'll talk about this calculator here that has these buttons and sort of the thing that you need to do to punch it in correctly. The other important sort of button you should look at on your calculator is your, I call it your negative button or change the sign button. So on most people's calculators, there's a plus or minus, or a lot of calculators, they have like a sort of negative type button. So you got one of those 2 kind of going on there. All right, so if we wanted to punch this in correctly into our calculators, this is what you should do. You should go 1, you should hit the decimal, 2, 3, then you should hit your exponent button. And depending on your calculator, it will probably look something like this, 1.23, it'll maybe pop an E. Or it may look like 1.23, pop up a couple of zeros. Or it might do both of this, 1.23 and like a small 10 to the 0 and pop up some zeros. So one of those 3 things should probably be happening on your screen at this point. When you hit the exponent button, what that button represents when you hit this button is this part of the number. So it represents that part of the number, the times 10 part of the number. That means when you are punching this into your calculator at this point, you don't hit the multiplication button. You don't do any of those things. All that is left is the negative and 3 that you need to put in there. So here is where we do our negative button and 3, and that will go minus 3 there. That will turn this guy into a minus 3 and turn this guy basically into a minus 3. And that is the proper way to punch a number in scientific notation in your calculator. You should never, ever, ever, one more time for good measure, ever use like your log button and the shift log button, which a lot of people like are fond of because it makes sense. When you look at your log button there, it's like a 10 to the x, so that seems kind of like scientific notation. It's not, by the way, that's the inverse log. And you'll be messed up, especially when you get to the acid and base chapters. And you'll find yourself, by the way, a lot of times when you punch in numbers and do calculations that involve scientific notation, you'll get an answer that looks really good, but like the exponent part's off by like 1 or something like that. And that's usually an indication that you're not punching it in correctly in your calculator. Either you're using like the log button there, or you're using the multiplication button in between. Now, if you have this type of calculator here, it's not a really big deal, except that the way typically these calculators are programmed, you got to put parentheses around every number that is written in scientific notation. So for example, if we're going to do the same one on this one, what you need to do if you have this type of buttons, you need to open a parenthesis. You need to go 1.23 and then hit your exponent button, which would be that 10 to the 9. And on your display, you'll have 1.23. It will pop a times 10. And what you'll have at that point right now is a blinking cursor up towards the top of the 10, and it's blinking at you. No big deal. You just continue on. You hit your negative button and your 3. And at this point, you will have a 1.23 times 10 to the minus 3 and a little blinking button still pointing at you up there on top. Now, the problem with a lot of these calculators is you got to fix that guy. He's up on top. You need to bring him back down. So that is where your little wheel comes into play. And pretty much if you hit this side of the wheel, that will bring this guy back down to a regular size sort of cursor. And now you'll have the regular size cursor. And then you could close your parentheses and you will finally, obviously there's a lot of steps because I'm just writing it step by step, but you could do this super quick. It doesn't really matter once you figure out how to do it, but that is what you should end up with. So that is what it should look like. Again, the oddly as it may sound on most calculators, if you don't do this part to bring the cursor back down and you do like a super small parentheses like this, usually you'll get an error because the parentheses is small. It's not over the whole thing. So you got to make sure you bring that down. So if you have either one, they all work the same. Just got to make sure you know how to properly do it because we definitely will come across a lot of numbers in scientific notation. And you need to know how to properly punch it into your calculator. If you're not sure at some point, just come by and bring your calculator. We figure it out together. But it's really, I would almost say more important than writing things in scientific notation is being able to punch it into your calculator correctly. Any questions on any of those there? Yeah. Well, in this case, we really didn't do a calculation other than just putting this number in. So depending on your calculator, it may turn that number into just like a decimal number or not, or it may just leave it like that. It kind of depends. So for example, let's do one where we're actually going to do some calculations with two scientific notations. So why don't you do this one on your calculator? Let's go 1.23 times 10 to the 6. Let's go minus 6, actually. Equals 6. Let's do minus 6. All right, 1.23 to the minus 6, and let's divide it by 4.2 times 10 to the 12. See what you get. And then let's do 3.33 times 10 to the minus 4. Multiply it by 1.9 times 10 to the, we'll go 5. See what you end up with. I'll do it as well because clear it. Question. Okay, so let's take a look and see. So again, if I was going to punch this in, I'd go 1.23. I would hit my exponent button. I would hit my negative button here and my 6. I would then hit my divide button. I punch the other one in the same way, 4.2 times 10. Not times 10, hit my exponent button. Hit my exponent button there. And since this is a positive exponent, I don't need the sort of negative button. And then obviously I'd hit my equals. If you have the other one there, you'll need to go parentheses 1.23. You'll hit your exponent button. You'll hit your negative button. You'll hit your 6. You'll do your will. And then you'll close the parentheses. You'll hit your divide button. You'll go 4.2, open a parentheses first. You'll hit your exponent button. You'll hit 12. You'll hit your will one more time to bring down the thing. Then you'll hit your equals. Whichever way you do that, hopefully, you end up with this number on your calculator there, 2.92857143. E minus 19. That is what my little display sort of looks like on my calculator. First off, any questions on how to punch it in there? All right, so let's talk about a couple things about cleaning it up here. We'll talk about, again, the significant figure rules in a second. So we'll take this to 2.9 times 10 to the minus 19. Now, it's really important when you take a number from your calculator, a couple of things. Obviously, it won't give you the answer to the proper number of significant figures, which we'll talk about the rules in just a second. But very commonly, people tend to forget to include that in their answer, the actual exponent part. So just like when we put an E there or we see an E, it represents the times 10 part of the number. That is what we need to make sure we put back into our answer there, and we don't just leave it at like 2.9. So that would be the incorrect answer here. So we want to make sure that we don't forget that last part here, and we turn it back into scientific notation. And we'll talk about a little later on here why we rounded to 2.9. But that's really an important thing. Sometimes people very commonly forget that part of it. They just kind of write the front number and stuff like that. Any questions on that there? Now, as I was talking about earlier, if you find yourself like, hey, I got like, this part good, but this part's just a little off, it's probably the way you're punching into your calculator incorrectly, stuff like that. So that's usually a really good symbol. You're like, I don't know, I'm always like one off on the exponent part. And that's usually an indication you're probably not correctly sort of punching in. All right, let's take a look at the next one. Next one, we're going to go 3.33. Going to hit our exponent button. We're going to hit our negative button. We're going to hit our 4. We're going to hit our multiplication button. 1.9, once again, exponent button. And 5 and equals. Obviously, again, if you have the other calculator, you're going to kind of do the same thing, except you need your parentheses. So parentheses 3.3 times 10 to the n. Our negative, our 4, bring our parentheses back down. Our multiplication, open a parentheses, 1.9 times 10 to the n, and a 5, again, our will. Hit that side, close our parentheses, and our equals. And depending on which way you do it, hopefully you end up with, we're going to multiply on that one, 1.9 to the 5. So I believe on my calculator here, I end up with like 63.27. In this case, there is no scientific notation given to me on my calculator. So it's just a regular number. And in this case, we would actually take it to 63. Any questions on how to punch it into your calculator in scientific notation? Yeah.
Why you went to a whole number?
I will. Yes. Yeah, definitely. So the quick explanation is, and we'll talk about it again, is basically when you're multiplying and dividing, the number that has the least number of significant figures is how many significant figures your answer should have. So when you're multiplying and dividing. It is different when you're adding and subtracting. We'll talk about all those in just a bit, but that's sort of the reason why. That's why up on top, if we look at those numbers, which are written in scientific notation, up on top, this has 3 significant figures, right? Because of the way it's written. This guy has 2 significant figures. So we took it to 2 significant figures there, the way we wrote the answer. This guy has 3 significant figures based on the way it's written. This has 2 significant figures. So that's really why we go to there, which is the smallest number of significant figures. Other questions? All right, so again, if you're not sure still how to use it at some point in the next couple of meetings or so, come see me and we'll figure it out together how to do it on your particular calculator. But that usually will take care of almost all calculators, I think. So take a moment here and write each of these guys in scientific notation correctly. Okay, so let's take a look. So here we want to go to the left here. That's going to give me 56.8, and one more gives me 5.68, which is a number between 1 and 10. And that would get me 5.68762 times 10 to the 2 in this case. There is a reason why we keep all those numbers, and the reason is significant figures. So when you write a number from scientific notation to regular form or sort of regular form to scientific notation, you never want to lose significant figures. So you should always keep the same number of significant figures. In this case, all those numbers are significant, so we do want to keep them when we write in significant figures, because technically speaking, 6 significant figures, 6 significant figures, we didn't lose anything along the way. Here we need to go 1 place, 2 places, 3 places, 4 places, 5 places, 6 places. 7.72 times 10 to the minus 6, again, small number, negative exponent in this case. Here, there's not a decimal point actually written, but we do assume it's here. So 1 place, 2 places, 3 places, that's 12.5. One more is 1.2, which is between 1 and 10. And that gives us 1.25 times 10 to the 1, 2, 3, 4. Here, again, it is significant figure-wise why we dropped the zeros, because they're actually not significant in this case. So we lose the zeros in this particular case. Here, we're going to go 1 place only there, and that will get us 1.35 times 10 to the minus 1. Any questions on that there? All right, so I think we'll skip that. So let's talk a little bit about measurements and uncertainty, and we'll get into obviously now some significant figures and all that kind of stuff. But when we take a measurement, no matter what type of measurement that you take, if it is a measurement, there's always some degree of uncertainty involved in that measurement. The degree of uncertainty in that measurement is based off of really the equipment that you use. So when you use a piece of equipment, there's a certain level of uncertainty associated with that. Some type of estimation is always sort of made depending on the device that you use. So let's just take, for example, if we had a ruler. Connect them here. We'll say this is centimeters, for example. And let's say we wanted to measure a arrow, for example, in this case. Now, whenever you look at any piece of equipment that you're going to use to make a measurement, be it a ruler, be it a graduated cylinder, a burette, any type of glassware, there's usually 2 types of sort of markings that you typically see. So one type of marking is what I refer to as the large markings. And the large markings are the ones that actually have numbers next to them. So they actually have some type of value next to them. So for example, in this case, we have a large marking at 1 and we have a large marking at 2. And the difference between 1 and 2 in this case represents 1 centimeter, right? So that's a 1 centimeter difference between them. The next type of marking that you typically see on a piece of equipment are what are referred to a lot of times as these small markings. And these small markings typically do not have any type of numbers associated with them typically. They are the markings that you find between the two ones that do actually have numbers between them. And we want to count up essentially how many of those little markings there are. Now, when we start counting, it's also really important that you start counting correctly. So typically speaking, you start counting the smaller markings after the last large marking. So for example, the 1 was our large marking, so we would start counting here. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, and we stop counting at the next large marking. So that would be 10 markings between our sort of large markings. That means each of the smaller markings in this case represents how much? There's 1 centimeter and there's 10 little markings between them. Each one represents the small markings. Yeah, each one represents 0.1 centimeters. If you're not sure, just divide that by 10, by the way. Yeah, you'll get basically that number right there. That means that if we look at this guy here, this is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then obviously 2 as we go over there. Now, once we sort of establish what's the large marking, what's the small marking represents, we're ready to sort of take our measurement. And there should always be a certain amount of numbers in your measurement that pretty much no matter who takes a look at it, everybody should agree that it is at least that amount. So for example, if we look at my arrow here, and we'll just call it, if I drew straightish, kind of down that way. So if everybody looks at this marking, everybody should agree that the arrow is at least 1.5. So we would record those because these are what are referred to in a measurement as all the certain numbers. And again, those are pretty much the numbers that no matter who takes a look at it, everybody should definitely agree. Now, if you look at my semi-straight line there, we could clearly see in this case that it's not 1.5. We could also clearly see, hopefully, that it's not exactly 1.6 at this case. So this is where really the uncertainty in the measurement comes into play. This is where the estimation is. Now, what most people will do is kind of imagine between those two markings where the arrow is. Okay, is it like halfway there? Is it not halfway? Is it a little bit more than halfway? So in this case, the way I drew it, to me, it looks a little bit more than halfway there, right? So it's a little bit more than half. So maybe you record something like 1.57 and then clearly the units with it. This number here is what is known as the first uncertain number. And that is where basically the estimation is. Somebody else may look at it and go, I don't know, I think it's just past half. Maybe it's like, 6 at the end there, or maybe it's a little further closer, or maybe it's like an 8 or a 9. So that is where sort of the estimation comes into play. Now, when you take a measurement, you should always record all the numbers plus the first uncertain number. And when you do that in a measurement, that is what we like to call our friends significant figures. Yeah. So significant figures is in a measurement where you record all the certain numbers plus the very first uncertain number, which means, by the way, this number would have how many significant figures? Has 3 significant figures in this case. The uncertain number, or the estimated digit in this case, is the 7. And usually what that pretty much means in most cases, it's like kind of like plus or minus 1 of that. So again, maybe it's 1.57, but maybe it's really like 1.58, maybe it's like 1.6. That's where the uncertainty falls in that sort of last digit. Any questions on that there? Yeah, so significant figures are basically derived from measured numbers, and they're derived from all the certain numbers in a measurement, and that first uncertain number is basically what make up what significant figures are. Yeah. So it does depend, for example, on the type of equipment that you're using. So for example, if we got A very badly drawn graduated cylinder here. You'll see why it failed art 9 times. All right, there we go. So that would be 10. 20, and we'll go milliliters on that. And we'll put like a liquid in there. So for example, when we have a liquid in a glass container, we typically will see the curvature of that liquid dramatically drawn there, oftentimes as a U. That's known as a meniscus. And a meniscus is the curvature of the liquid. We'll talk about it in a later chapter, but essentially what's happening is the attractive forces between the water, for example, and the glass are actually stronger than the attractive forces between the water and itself. And capillary action has the water at the edges in contact with the glass start to rise up on top. And that causes that kind of U effect in most cases. When we read a volume, we always go from the bottom of the meniscus. And that is because that is where the actual volume actually is as a result of not having that effect of it crawling up the sides of the container. If it didn't have that effect, the sides would come back down to basically where the middle is, where it's not in contact with it. So we always read from the bottom of the meniscus. I would say probably 99 times out of 100, that is what your meniscus is going to look like. It is possible, for example, mercury goes opposite. If you look at something that has mercury in it, its meniscus will actually go the other way. In that case, you would actually read from the top of the meniscus in that particular case. In the case of mercury, mercury is strongly attracted to itself versus the walls of the container. So it actually comes in on itself and travels downward rather than upwards. Most liquids that you put into a glass container will do that U, sort of, it will travel upwards, but it can go in the other direction. So most of the time we do read from the bottom of the meniscus. Once again here, we're going to look at our scale and our large markings in this case. We got 10 and we got 20. That is going to be 10 milliliters in this case. Again, we're going to count the smaller markings between those. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, here we have 10 markings between the two larger markings. That means in this case, each of the small markings represents how much in this case? 1 milliliter in this case, right? Again, if you take 10 divided by 10, you got 10 markings, you'll get 1 milliliter. That means this guy's actually 11, 12, 13, 14, 15, 16, 17, 18, 19, and then obviously 20 up there on top. So if I take a look at my meniscus and go from the bottom of my meniscus, again, we could see it is definitely 15. Everybody should agree upon that. We should record 15. Not exactly 15, not exactly 16. Again, maybe you feel it's a little bit above halfway there. So maybe you record 6. Again, certain numbers. First, uncertain number. And our units, which are milliliters in this case. And this would be the proper way to record this value. This would have how many significant figures in this case? It would have 3 significant figures in this case again. Yeah.
So that first a certain number counts as a significant figure.
Yes, and that's when you're taking a measurement, that is pretty much where you should record to. The idea behind that is essentially, as we'll talk about when we do calculations and significant figures, your calculation, for example, is only as good as your worst measurement. And we could identify kind of where our worst measurement is based on how many significant figures there are. So, you know, that's where the first uncertainty happens in that measurement. That's kind of where it's the worst. That's as far as you could go until it gets really, really bad, right? So you only want to record that first one. Now, it does depend. So, for example, here, if we have a graduated cylinder, no quality control at that factory, apparently 10 milliliters here. 20 milliliters, and we'll go like right there-ish. All right, so in this case, my large markings would represent 10 and 20, still 10 milliliters. In this case, if I take a look at what I got going on between, I got 1, 2, 3, 4, and 5 in this case. That means each of my smaller markings in this case represents how much in this case? 10 divided by 5 is? That's not the hard question. 10 divided by 5 is? Grab your calculator if you're not sure. 2 milliliters. Yes, I think, yes. So this is 2 milliliters in this case. Again, if you divide this by 5 markings, you end up with 2. That means this guy's actually 12, 14, 16, 18 in this case, yeah? So when we go to record this and we look at where we're at, I am now between 14 and 16. What number comes between 14 and 16? 15. This would be the proper measurement here. That would have how many significant figures? 2. Which one's the uncertain number in this case? It is 5. That would be our uncertain number in this case. That's the best you could do. The reason that's the best you could do in this case is you got basically 14, you got 16. There is no way to know kind of where 14 stops and 15 begins in that little space because it's too many numbers between them, right? So the best you could do in this case is a whole number. So you do want to make sure that you always sort of figure out the scale. It does differ depending on the equipment. You may have a 10 milliliter graduated cylinder that's made by company A, and you may have one that was made by company B, and they put different markings on them, and they may actually have different scales. So it's really important. I've seen that in many chemistry labs, like they bought them from different people, and half the class has ones that go like to the second decimal place, and half go the first, and stuff like that. So they try to get everybody the same these days, but years ago that it was very common and stuff like that. So it's really important to take a look at it, even if it's like something that somebody next to you is using that's kind of the same volume or whatever it may be. It may actually have a different scale. Now, first off, any questions on that? I would say the general rule is how far should you take the measurement to is you usually could go one more place to the right of the smallest marking. This you cannot. The smallest marking here is 2. We can't go any more to the right of that. But if you go back to this one, the smallest marking was 1. We could go our whole number. We could go one more place to the right of that whole number. The original one that we looked at, the smallest marking was 0.1. We could go one more place to the right of the smallest marking. So typically speaking, you could go more place to the right of the smallest marking. Not always, as we saw in the last example there. How can you figure out how far you should take the reading to? Well, if you can confidently know what the smallest marking represents, you could take the smallest marking and divide it by 2. And if you do that, that will get you 0.05 centimeters plus or minus. They sometimes want you at the school to record that as the tolerance or uncertainty in the measurement. And you would record something, for example, of 1.57 centimeters plus or minus 0.05. And that goes to 2 decimal places. That is where the measurement should go. So if you're not sure, but you are sure about the smallest markings, just divide it by 2, however many decimal places or wherever that number comes to, that is what your measurement should look like. So for example, if we come here to this one, that's 1, we divide it by 2, gives us 0.5. That's plus or minus 0.5. That is 1 decimal place. That's exactly where we took the measurement to. And you can record this 15.6 milliliters plus or minus 0.5 milliliters. And again, 1 decimal place, that's where we should take the measurement to. It even works for our last one that we did here. If you divide this by 2, you end up with 1 milliliter. And this is plus or minus 1 milliliter. And that's what we did. We took it to the whole number there. And you would have 15 milliliters plus or minus 1 milliliter as the uncertainty in the measurement. And that is how you could record that. Question on that. So if you're 100% sure what the smallest marking is, right? But if you're not sure of that for sure, smallest marking divided by 2 will tell you basically how far you can take the reading to. When you're asked to include the uncertainty or the tolerance there, or accuracy or precision of the measurement, that's what they're talking about, this kind of plus or minus sort of number with your measurement. Any questions on that there? Now, let's also talk about a very common thing that people perhaps, I'll just draw a new one here maybe, do, which is very common. We'll take our ruler like we had at the very beginning, same ruler basically. And let's just say we had an arrow here dead on that marking right there. And as we saw earlier, our large markings here is 1 centimeter. We still have our 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. Our small markings, because there's 10 markings between them, is going to be 0.1 centimeters. Now, if it's dead on that marking, what should we record? Should we record 1.3 centimeters, 1.30 centimeters, 1.300000 centimeters for good measure? Doesn't matter what you record. Well, let's take a look at 2 of them. By the way, too many, not good. Just say no. So too many zeros, not good. Too few zeros, maybe not good in certain cases. So let's just take each of these and see if there really is a difference. So if I have 1.3 centimeters, right? That, by the way, would have how many significant figures? Would have 2 significant figures, right? The uncertain number here is the 3 in this case, right? That means what I'm really saying is I think it's 1.3, but it might be like 1.2. It might be somewhere like 1.4, as that is where my uncertainty is. That's basically a span from here to here. When we look at where it is in the picture, it is nowhere near any of those numbers, right? That is a lot of uncertainty you just put into that measurement, right? Now, if we take a look at this number here, how many significant figures does it have? It does have 3 significant figures. Which one's the uncertain number? It is the 0 here, right? That's the estimate. So when we take a look at this one, it is 1.30 centimeters, but basically you're saying, I think it's 1.3. Maybe it's 1.31. Maybe it's like 1.29. That is, I would say, like kind of in this range here, right? Which one's a better measurement based on the scale? It is this one, yeah? And what you're doing, even if you don't think about it, you're like, the 0, that really doesn't matter. What you did if you did this move is you just created a lot more uncertainty. You made your measurement a lot more crappier, if you will, yes, than it was originally. It shouldn't be that crappy based on the scale, right? It should be a lot better of a measurement than 1.3, because you have the ability here to go to the second decimal place. And by losing a 0 here, you're actually making the measurement a lot worse than it should be, and you're making that number a lot worse. The same effect also occurs on the other side there where I crossed out originally. If you put extra zeros, you're telling people, for example, if we had this guy, that the uncertainty is way over here, you're saying like this measurement is way better than it should be, right? You put too many zeros in there, and you're actually making it a lot better of a measurement than it can be with the scale that you're using. So it's really important that if you hit something right on the nose, because you have the ability to go out that far, you should put a 0 there and keep the measurement correct. Again, you can get that by dividing this by 2. That will get you 0.05 centimeters, 2 decimal places. That is where you should take it to. So again, it kind of tells you where you should take it to. And technically, this should be something like 1.3 centimeters if you include the uncertainty, plus or minus 0.05 centimeters is the right sort of measurement. But it should go to 2 decimal places in this case and have 3 significant figures. So it's really important not to lose zeros, not to cut off things, because you're actually making your measurement a lot worse. Also, you shouldn't add zeros because you're making your measurement a lot better than it can be. You do have to look at the scale and get it to exactly what it should be. Question on how to take measurements and where significant figures come from. Now, if you are taking a measurement of anything that is digital, all the numbers are important. So they wouldn't be there if they're not important. So anything that is digital, like the balances, the scales in the lab room, if it gives you a digital display of what it is, you should record all the numbers. That's also a very common mistake people make. They go to the balance and go, it's like 52.15, they just write 52, right? So you don't want to lose any of those numbers for the exact same reason. You're making your number either worse or better if you put things in there. And that's going to affect overall your calculation at the end, which is based on proper number of significant figures. So if you don't have proper number of significant figures in your measurement, when you go to do calculations with it, you're going to end up with a wrong answer in terms of significant figures of your answer because you screwed it up at the very beginning when you took the measurement. Any questions on that? Yeah.
Example, it was 1.3, when you divide it by 2,
Mhm.
that just tells you how many decimals you need.
Yeah, I personally would use it for that as to how far you should take the reading, how many decimal places. It is also, they refer to it here in this department as like the uncertainty in the measurement, or sometimes they'll tell you include the uncertainty in the measurement, and that's where you would write the plus or minus 0.05. For me, I'm more important probably the first part of the measurement there, but you will see that asked to be as you go through your chemistry classes. When you're in lab, they want you a lot of times to include the uncertainty in any measurements that you make, the plus or minuses and all that kind of stuff. And that's how you'd get it, basically smallest marking divided by 2. That's how you get the uncertainty in the measurement, and it also tells you essentially how far you can take the measurement to. Yeah. Most people consider it kind of plus or minus 1 of that uncertain digit, but technically speaking, there's that kind of span of, how far it could be off. Yeah. Other questions? All right, we're laid up there for today.